In an effort to give the organizers a break after having already organized everything, I think we're going to pass around the chairing responsibilities, so you're stuck with me for this morning. The agenda is we have Tom Britton speaking from 9:30 to 10:30, then we have a break for 45 minutes until 11:15, and then we have Maria Deshpan back there who will speak until noon. So very pleased that they're able to have Tom come here to speak with us. Tom is a longtime expert working in probability and statistics of epidemic processes, particularly with an emphasis on networks. He has several books on the topics and many papers. He's going to talk to us about network epidemic models with preventive rewiring.
Thank you, Eric. Is the microphone on? Okay, that's good. So my plan was to talk for about 30 minutes, then I was given a 45-minute slot, which last week was changed to an hour slot, so maybe I should speak much slower from now on, or else I will finish early, but I guess that's all right. Anyway, thanks to the organizers for organizing this nice workshop. So I will talk about a disease spreading model that takes place on a network. And I can't say that it's very novel, but the one novel thing is that the network will change as an effect of the outbreak. So that's the possibly new thing. I will tell you more about it. It used to work, but maybe I should use... No, nothing works here. Not that one doesn't work either. Yeah, that's good. That's perfect. Slow down. All right, thank you very much. Yeah, so here we go. So the aim is to study how adaptive or preventive behavior can affect disease spreading, hopefully reducing disease spreading. And what we will do is we will have an epidemic that spreads on a network, and the network is there in order to describe the social structure of the community. And to study how distancing yourself from infected people, how that can affect disease propagation. And more specifically, we have a disease. You can think of that as a fairly serious disease, so you really don't want to get infected. And then if you are a friend with an infected person, maybe you stop seeing that person. That's the idea. It could be that you stop seeing that person, or that you sort of replace that friend with a new friend. Probably, I don't know what is reality, but maybe it's a mixture of the two. And we have a parameter which sort of tweaks this. So either you just drop the edge to the infected person, or else you replace it with probability 1, or you could do sort of 50-50, that some you drop and some you replace. And this model is, at least to us, sorry, it's not my own work, it's together with two people from University of Girona in Catalonia. So we haven't managed to analyze the whole process, so we mainly focus on the beginning of the epidemic. I don't see that as such a big problem, because I think most serious epidemics, they stop early on. They never infect 30% of the community. They only affect 1 or 2%. For instance, Ebola. So that we only analyze the beginning of the epidemic. I don't see that as too big of a problem. But of course, it would be nice to analyze the whole epidemic. And we do this using two different methods, the branching process approximation and a pair approximation. So we also see how these two methods work, and when they are similar and when they're not similar. Okay, so now let me define the model that we study. So we use a toy model for the network, the configuration model. Of course, What type of network you should have depends on what type of disease you're considering. If you're considering Ebola, maybe households play an important role and other close relatives, whereas if you're interested in a sexually transmitted disease, maybe something like the configuration model is more realistic then, at least if you consider it spreading on a homosexual community. But the type of network you should use will of course depend on what type of disease you're considering. So if you want to have something in mind, since we use a configuration model, maybe you should think of a sexually transmitted infection. And I don't have different individuals, so maybe you should think of it spreading in a homosexual community. I think most of you know what the configuration model is. So you have some degree distribution that you believe describes the number of friends that the individuals have, and you construct it by giving each node an IID degree, and then you write out some stubs, and then you connect the stubs pairwise, and it's known, it's been studied extensively by many people, and it's known that as the number of nodes tends to infinity, the problems will become negligible, so there will be very few self-loop and multiple edges if the degree distribution is nice enough. So anyway, this is the network that we study the epidemic on. Of course, you can criticize that, and that's something we would like to extend to more to other types of networks, but for now we have the configuration network, and it is defined by a degree distribution. So in the limit, most of you probably know, there will be no short loops and there is no degree-degree correlation. Maybe a bit unrealistic, but that's a consequence of the configuration model. So that is the model for the social structure in the community. It's a static network. So the network is not dynamic as suggested by the theme of this workshop, but there will be a little bit of dynamics coming later on. So we have a static network, so I've written a static network there. And then on this network, a disease spreads. We look at two different types of disease models. One is called SIR and one is called SEIR. S is susceptible, I is infectious, and R is recovered. Recovered means that you're also immune for the rest of the study period. So individuals are at first susceptible. If they get contacted, if they come in close contact with someone that's infectious, they get infected and immediately become infectious. And then while they're infectious, there is a risk that they transmit it to their neighbors. And after some random time, they stop being infectious and they recover and are immune. So that is the disease model. The SEIR is where you get infected, but it takes a while until you start spreading the disease onwards. E stands for exposed, but nowadays it's usually called a latent state. So you have been infected already, but you typically don't show symptoms, and you don't spread the disease yet. So something builds up in your body, and only after, let's say, 5 days, you become infectious. For many purposes, these two models behave very similarly, but they will turn out not to behave similarly on when people start taking preventive measures. So that's why I distinguish between the two models. We look at the Markovian version of it, meaning that everything is exponential. So your infectious period is exponentially distributed, and you infect your neighbors at rates. So that's not fully realistic. Usually the infectivity, a constant rate. You infect others at constant rate over your infectious period, whereas in reality probably you have low infectivity in the beginning, then it goes up a little bit, and then it fades off. But we have a constant infectivity during the infectious period, and that infectivity is called beta. In the SEIR case, you're first latent, and then you leave the latent state and jump into the infectious state at some rate phi. And once you become infectious, you infect others at rate beta, and you recover at rate gamma. So this means that the probability that you will infect a given neighbor during your infectious period, since it's two competing events, either you recover at rate beta or you infect that person at rate you recover at rate gamma and you infect your neighbor at rate beta, so the probability that you will infect your neighbor before you recover is beta divided by the sum of the two. So is this model clear? Okay. Sort of a standard model. Markovian is of course for mathematical tractability, not for realism, and maybe I forgot to say that. So we have a homogeneous mixing with your neighbors in the sense that during your infectious period you infect at constant rate, but also you infect all your friends at the same rate. You could think of situations where you have like a weighted network, so you have some closer friends that you meet more regularly, that you have a higher infection rate, and others that you meet slightly less frequently with a lower infection rate, but we have the same infection rate for all individuals. Anyway, if we stop here, then this model has been studied extensively. That comes 2 slides from now. So the model looks like follows. Here we have this network. Maybe we start with one infected individual, this red person. This individual infects each of the 3 neighbors at rate beta. So maybe eventually this person becomes infectious. And maybe after some additional time that person becomes infectious. But then this individual recovers, and let's assume recovered is green. So now these 2 people infect their neighbors at rate beta, and so on. They cannot infect back because this person is immune. So maybe it goes like this. Okay, this model has been studied before, but now the new thing is that okay, so let me just stress. The network is static, but the disease or the epidemic process is dynamic. So it's something dynamic that goes on a static network. But now we make the network also slightly dynamic in the following sense. An uninfected individual that has an infected neighbor might drop this edge. So if this is me, I see that my friend is infected, maybe I drop this edge. Maybe I drop it, or maybe I choose a new friend, maybe that friend instead. So either you drop the edge, or you connect it to a new edge. And you also do this at rate, in the sense that maybe you don't observe exactly when the person was infected, but at some stage or at some rate you observe that the person infected, and you decide to stop socializing with that person. And the rate at which you remove the edge is omega, and the probability that you rewire is called alpha, so that's probably listed here. So omega is the rate at which a susceptible individual drops the edge to an infected neighbor, and alpha is the probability that at the same time you drop it, you connect to someone else. So if alpha is equal to 1, it means that you always rewire, whereas if alpha is equal to 0, you only drop. And you can of course have alpha equal to 0.5 if you prefer. Yes?
Rewiring is conditional only on your neighbor getting infected.
Yes.
Correct? It's not happening in general.
No, you only rewire if, yeah, that's a good comment. So you only rewire if your friend is infected. We haven't, but I don't think it's all that much more complicated. But you could have the sort of the network in itself also being dynamic. But if you did, you would have sort of an additional rewiring rate to your infected person, and that would still make it more complicated to analyzing. If you sort of rewire randomly, that's a much more easy thing to deal with modeling wise or analytically. So do you understand this? Sorry, yes?
Randomly selected individual, uniformly from the population?
Yes. And since we will look, I'll come back to that, but we look at the beginning of the outbreak, so with a large probability you will connect to someone that's susceptible. So is the model clear still? All right. How about the SEIR situation then? So what I just described was for the SIR, but for the SEIR, things will depend on how do you do if your neighbor is exposed but not infectious, and how do you do if yourself are exposed and not infectious. So for that reason, we have now, making it slightly more complicated, we have 3 different rewiring rates, where the first index refers to the person that will potentially rewire, and the second index for the person that he or she will rewire away from. So you could have a rate if you are yourself susceptible and the other one is latent, possibly you rewire away from that person. Let's call that rate omega SE. This is what was in the previous model, so you are yourself susceptible and your neighbor is infectious. And then this thing, you have already been infected, but you're exposed, you're latent, so maybe you don't know this, and still you rewire away from your infectious neighbor. And as before, alpha is the probability that you rewire. So if so we have 3 different rewiring rates. Of course, they could be any numbers, all 3 of them. If I was to think about realism, one possibility is to treat exposed as you have no symptoms yet, and then yourself you don't know that you have been infected, and others don't know that you will have been infected. And if that is the situation, then you will not rewire away from an exposed neighbor because you don't know that person is infected. However, you will rewire away from an infectious person whether you are susceptible or exposed, because you have already been infected but you don't know this, and still you rewire away from your infected neighbor. So in terms of realism, I guess this might be a natural thing, so that this one is 0 and these 2 are identical. But in general you can have all 3 being different, and that's what I'll treat the general situation. Yes?
Is it later something, the first and the third look the same to me.
Sorry?
Is something, the definition, I missed something, I think. The first and the third.
The third is wrong, I think.
One of them, I think, must be slightly.
Is the third one wrong? Is this one wrong?
Is it exposed or infected?
Yeah, so sorry, it should be
Should be exposed.
Exposed to an infection.
yeah, you're right. It's an exposed individual drops an edge to an infectious neighbor. That's thanks for commenting on that. Yeah, you're completely right. Are the other ones correct? Susceptible, exposed, susceptible, infectious. Yeah, so here it should be exposed, infectious. Sorry about that. All right. Thanks, Frank. Okay. So to summarize, we have a few parameters, maybe too many. I think I prefer models with 3 parameters or so. But beta is the transmission probability. Phi only applies in the SIR. In the SIR case, you don't have that many parameters. You have beta, gamma, and the mean and the variance of the degree distribution, and 1 rewiring rate, and of course this probability to rewire rather than the dropping. Whereas in the SEIR case, you also have a rate at which you move from the latent state to the infectious state, and you also have 3 different rewiring rates. Okay. So let me first summarize some results for the situation when there is no rewiring. Then it is known that as the population size n tends to infinity, the epidemic behaves like a branching process over finite time horizons, actually even slightly growing time horizons. And if you have studied infectious disease model, the perhaps most important parameter of all is the basic reproduction number. The interpretation of it is how many people a typical infected person infects during the early stage of the epidemic. And in our situation, it is how many susceptible neighbors a typical infected has multiplied by the probability that you infect one of them. And this first part, the probability that you infect the neighbor, I already described earlier. It's this. And how many susceptible neighbors do you have if you're an infected person in the beginning? Well, it is the expected value of the size biased degree distribution subtracted by 1. What does this mean? It means subtracting by 1 follows from the fact that you have been infected by one of your neighbors and you cannot reinfect that person. But in the beginning, all other neighbors of you will be susceptible. So that is -1. But what is d tilde? Well, the fact is that in the beginning of an outbreak, so if these are 3 individuals, who do you think will get infected in the beginning of the outbreak?
Third one.
The third one, yes. The third one is 3 times more likely to be infected than this one, and this one we know will never get infected. So the degree distribution of infected people in the beginning is different from a randomly chosen person. And it is different in the sense that individuals with degree 3 are 3 times more likely to get infected compared to individuals with degree 1. So it is a size biased distribution which depends on the original one. So this is k times pk. This is the number of edges you have multiplied by the fraction of individuals having that degree. So that is the basic reproduction number. The probability to infect a neighbor multiplied by the expected number of susceptible neighbors a typical infected has in the beginning. You can rewrite this in terms of the original degree distribution as follows, and in terms of the parameter it looks as follows. And an important observation made about 15 years ago was that this thing here is infinite if the variance of the degree distribution is infinite. So if you have a degree distribution which has a very heavy tail, you will be supercritical always, which also means that it doesn't make any difference if you vaccinate 50% of the community, you will still be supercritical. Also, the final size for this model has been analyzed using something called susceptibility sets. I will not go into that, but that has done with Frank Ball and the collaborators. So quite a lot is known about this model without rewiring. But now let's go to the situation where you have rewiring. And all I can say is that it's more complicated, at least it was for us to analyze. Maybe someone else can find it's possible that you can come up with a nice trick to analyze the whole epidemic. And the reason is that individuals change behavior depending on the local features of the epidemic. So not randomly, but it depends on how the epidemic spreads, the network will change accordingly. So we only studied the beginning of the epidemic, and that makes it easier for the reason that nearly all individuals are then susceptible, and all neighbors of infected people are susceptible except the one you were infected by. And we use this in doing 2 different types of approximations. I will talk more about branching process approximation. The reason is that that's my home territory, whereas I know less about pair approximations. So also this model with rewiring, you can analyze, it will behave like a branching process if the population size tends to infinity. And the reason is that if you have a large if you have a very large network and you look at the beginning of the outbreak, then most people are susceptible, and also your friends, except the ones you were infected by, are susceptible. And you know the degree distribution of people get infected. It is this size bias degree distribution. So you sort of know the structure of the underlying branching process. So newly infected people, I will just briefly describe how that's done. Newly infected people have degree distribution d tilde, this size bias degree distribution. When someone gets infected, one of its neighbors is already infected, whereas the others are susceptible. Oops, there's an E missing here. And so if I get infected, maybe from here, I have 3 friends accordingly here, and then I might infect them, each of them. I might recover, but now also there is an additional stopping of spreading, in the sense that my neighbors might rewire away from me. So what is the probability that I infect one of these neighbors? Well, it's just simply the ratio of the infection rate divided by the infection rate, the rewiring rate of that individual, and the recovery rate of myself. So the new reproduction number is very similar to the old one, except you have added this rewiring rate. Maybe worth noticing is that the parameter alpha did not come in here at all, because you remember this individual rewires at rate omega, but it connects to someone else with probability alpha. But that connection, well, first of all, that person will not have been infected, and the connection will, with a large probability, be to someone who's susceptible, so it will play no effect. So we have the reproduction number for this new model. The BP stands for the branching process approximation, because we will have another approximation using pair approximation. So BP is branching process. Can we say more about this model? Yes, we can. We can also, using branching processes, say something about how quickly it grows, and we can also say what will be the degree of the typical degree of infected people, not when they get infected, but later on in their infectious period as well. So we can compute many different things, and the most important quantity in order to do this is to derive the rate at which an infected person infects new individuals t time units after he or she was infected, because that is something that will determine the growth rate. So let's briefly describe this. So what is the rate at which you infect new people t time units after you are infected? Well, you must infect one of your susceptible neighbors, and it's equal, because it's the mean rate, it's just multiplied by the number of susceptible friends you have, and you infect the person at rate beta, but you should not yet have infected, the individual should not yet have rewired, and you should not yet have recovered. So this is the rate at which you infect new individuals. So this will determine the growth rate of the branching process according to this equation. So the growth rate, it will grow exponentially at the rate r, where r is a solution to this equation. And you can solve this and you get an explicit expression, maybe not all that clarifying, but anyway, you get an explicit expression for that, and you can also compute, which could be of interest. So infected people, how many neighbors do they have during the beginning of the outbreak? And you get an expression for that as well, because that tells you something about how they will spread onwards later on. So that was not all that surprising results, but now it will be a little bit more surprising when we look at the SEIR model. Well, the methodology is not very different. Of course, things become slightly more complicated because you have more parameters. You get an expression for the basic reproduction number, which looks like this. Maybe I should have said something about the reproduction number. So let's look at this reproduction number for the SIR model. So this quantity, how does it depend on the different parameters? Well, of course, it grows, the reproduction number grows with the number of friends people have, in particular the size bias degree distribution. It grows with the infection rate. It decays with the recovery rate. The quicker you recover, of course, the lower is the basic reproduction number. And as expected, the quicker people rewire, the smaller is the reproduction number. So if people rewire away from infected people, that will reduce the reproduction number, as expected. It's not as obvious when you look at things here. How does this thing depend on different parameters? It increases with infection rate, as expected. It increases with the size bias degree distribution. It decreases with the rewiring rate that susceptible individuals rewire away from exposed. Maybe this is 0, so maybe not that important. It decreases with the rate at which susceptible individuals rewire away from infectious neighbors. However, the reproduction number increases with the rate at which people that have been infected rewire away from infectious people. So that is the, and I think this could be also in reality. So you have already been infected, but you're not aware of this, and you rewire away from your infected neighbor and connect to someone else. That means you can spread the disease onwards to that individual. So it's completely logical behavior of the individual, because he or she doesn't know that he has been infected. And you see your maybe your sex partner starts showing symptoms or something, maybe your temporary sex partner, let's say, so you go to someone else. But you have been infected, so it means that there is a risk that you will transmit the disease onwards. So that type of rewiring is harmful for that will enhance spreading of the disease. And I think this could actually happen in reality. So that is sort of slightly surprising. Once you see this, of course, you realize that this should be the case. You can also compute how the epidemic grows, and you can compute how many neighbors infected people have, and so on. And the growth rate will also be decreasing with these rewiring rates, but increasing with this harmful rewiring if you're exposed and you rewire away from infectious people. So how about pair approximation? How does that work? Well, I think several people here know more about pair approximation models than I do, but anyway, it is a deterministic model trying to keeping track of the number of susceptible, the number of infectious, and the number of recovered, but also the number of pairs of susceptible, the number of pairs of susceptible infectious pairs, connected pairs, and so on, for all combinations. Unordered pairs, so there is no IS, it's only SI. And then you would have to keep track of the number of triplets, the number of quadruples, and so on. But the idea is that you approximate the triplets. So how many triplets are there where the central node is susceptible, one of its neighbors is susceptible, and the other neighbor is infectious? Well, that will depend on how many pairs there are susceptible, how many pairs there are susceptible, infectious. But then you have 3 susceptibles here, so you have to divide by the number of susceptibles, and there's a constant in front to keep track of that, so that you get the correct numbers. I don't want to write down what these constants are, but for each triplet, looks like this. The number of triplets with a central susceptible is the number of pairs where susceptible infectious, and the number of pairs susceptible recovered divided by the number of susceptibles, because here you have 2 susceptibles and here you only wanted 1 of them, and multiply by a constant. And then you have you set up the differential equations for these quantities, and that will depend on the triplets. The differential equation for these will depend on the triplets, but then you use these approximations to close the loop, and you get I'll just write down, so you get a certain number of differential equations. So for instance, this one is not very surprising. How does the number susceptible change? Well, it depends on, it decreases at the transmission rate beta multiplied by the number of pairs of SI, connected SI individuals, and so forth. So here we see there are no triplets, but we have replaced them by the corresponding pair approximation. If we analyze this model and linearize in the beginning, saying that this quantity will stabilize, whereas the number of susceptible infectious pairs is very small compared to the number of susceptibles, then you can get, I wouldn't call it a basic reproduction number, but a threshold parameter using this pair approximation, and it is, so this is how many susceptible neighbors an infectious individual has on average, assuming that it stabilizes, as I said, and this is the rate at which this increases, because an infectious individual recovers at rate gamma and infects at rate beta, so this is the increasing rate, and that will be a reproduction number. And you can also compute the expected number of neighbors that an infectious individual has, and you get an expression which was actually identical to the one for the branching process. You can do the same thing, but it's more complicated for the SEIR, where you're also latent. So it's not very... anyway, you can do it, but it's a bit more complicated. And then, so then the question is, we have 2 approximations for this stochastic model. How do they compare? And the conclusion, if you analyze it, is that for the SIR model, when there is no latency period, and in particular no problem with this bad rewiring, then the 2 reproduction numbers are equivalent. They're not the same, but they're larger than 1 at the same time and smaller than 1 at the same time and equal to 1 at the same time. So they have both the same threshold phenomenon, because I forgot to say this, but the reproduction number equal to 1, that's a critical situation. If you on average infect more than 1 person, it means that the epidemic can take off, whereas if you infect less than 1 person, it means the epidemic will never take off. And you have the same degree distribution among the infected people in the beginning. So what we have done on the next slide is that we have plotted these 2 expressions. One is the basic reproduction number, another one is another threshold parameter, so they're not really comparable. And we have plotted them as a function of beta, keeping all other parameters fixed. In particular, we kept the size bias degree fixed at 10. And we also simulated outbreaks and looked at how many people infected during generation 2 up to 5. And we did that, as explained further here. So here is beta. As we increase beta, of course the reproduction number increases. We see here is the pair approximation, and here is the branching process approximation. And what are these dots? Well, the dots are simulations in a community of 10,000 people, not 1 outbreak, but 250 outbreaks, and we look at the mean number of infected persons that infected people infect during generation 2 to 5. So that's still in the beginning of the epidemic. And why not generation 1? Well, generation 1, we start with the randomly selected people, so they will be atypical. In later generations, they will have a higher degree distribution. So we see that this branching process fits fairly well with the simulated values. And how about the SEIR case? Well, then actually the two approximations give different results, and the branching process approximation is rigorous in the sense that we can prove that it converges. So this means that the pair approximation is wrong in the rewiring model for the SEIR situation. And of course, numerically it's not all that big difference, but we see that here, this is when there is no harmful rewiring, then the two models are identical. And we see that they cross the value of 1 at the one spot, whereas here we see that they don't cross the critical value 1 at the same spot. So it can be shown that the pair approximation underestimates the critical parameter. So let me summarize. This was sort of a fairly detailed study of a small problem, but anyway, what conclusions did we make from it? Well, one was that this rewiring could potentially be harmful. I think that's sort of one message to learn, that if people rewire away, they could already have been infected, and then that's actually, it doesn't hurt them to rewire in the beginning, because well, if they have been infected, they've already been infected, and most likely they will connect to someone who's susceptible. So from their own point of view, it's not harmful to do that, but from a public health point of view, it could be harmful to rewire away, and that's could be a message to learn. The two different approximations are equivalent, except when you have this harmful rewiring, that you rewire away if you're exposed, you still rewire away, and in that situation the pair approximation is wrong. But of course the pair approximation has a big advantage, that for that model you can analyze the whole epidemic, maybe not at least numerically you can sort of integrate it to the end and see what happens, but my suspicion is that it will not work all that good, but we haven't studied this in detail. So what are the things that we sort of the general goal that we want to do, or at least I want to do, is, because I think most serious outbreaks you never see big fractions getting infected. So the question is, why are there no big outbreaks? I think maybe public health plays a role, but I think individual protection is the most important factor, would be my guess. And something that I strive for is to look, first of all, from a modeling point of view, try to sort of bring in different types of preventive measures to see how that affects things, but then eventually going over to inference to try to estimate things, to see what preventive measures seem to be successful and which ones affected the stopping of the disease at most. But this more minor type of future work is, of course, we could look at other types of preventive measures, or that you could have increased preventive measures. Of course, the more you hear about people dying of Ebola, let's say, of course, the more protective you tend to be. So your behavior changes over time. It's not that suddenly you have an infected neighbor, but probably more and more when you hear about it, you change behavior more and more. And of course, adding some structures to the network is another important factor. Maybe we should have clustered network, maybe household models, maybe some assortative or disassortative features. Maybe we should have space or blocks or communities, sub-communities. We could, of course, let the network in itself be dynamic. I don't think that is will complicate matter very much, but that would still be an important generalization. And of course, it would be nice to not only understand what happens at the beginning, but also later on. But my general goal is to try to make inference for these type of things from real epidemics. So I prepared for 45 minutes, and that's what it is.
I guess sort of to the points on your last slide, do you think that what you've learned from this line of work tells you more about the model or about what we understand about epidemics, and then does that tell you whether do you think you can generalize any of the conclusions to more sophisticated models? So in other words, I guess what I'm asking is, what types of results do you think are likely to transfer in spirit to more realistic or more structured models?
Well, that's a good question. I can't say that there are more people knowing reality more than me, but I think this rewiring, now that we have thought a little bit about it, I also think that in reality, some of the protective measures that people take might be harmful from a spreading point of view, which I didn't really believe in before. So that's, at least to me, an insight. Maybe other people already have known about that. But it's a different thing. You protect yourself. I think most people are most concerned with themselves, but that could be harmful for the rest of the community. So that's something, at least I learned from it. I don't know if that answered your question, but
Yeah, I mean, or another way to ask it would be, if you were going to use the same method of attack for a slightly more sophisticated model, in which direction do you think it would be most promising technically to extend the model? There's another way to think about it. I mean, if you take the configuration model and maybe I don't know, add a little bit of clustering or something like this, do you have a sense of what the next points of attack are likely to be if you wanted to build up the model setting to something slightly more sophisticated?
well, I think one thing is this, that most epidemic models, you know, the literature estimates R naught, and typically they say that it's 1.5 or 2.0 or something like that. And if it is 1.5, then that says that if the community is initially susceptible, then more than half of the community will be infected. And it's very, very rarely that you see this size of outbreaks. And I still think the estimates of R naught are correct. So I think the main reason why we don't see this is that people change behavior. Once in a while, maybe public health measures play a role, but I think the main reason why we don't see the big outbreaks that would be predicted from the R naught estimates is that people change behavior. And the rewiring, how do they change behavior? Well, wash their hands maybe if it's influenza, using condoms if it's HIV, staying home if it's influenza. So try to bring these things into the modeling, and at the later stage doing statistical inference for it. I think that is a very important thing to do.
I mean, I guess the interesting thing there is when the time scales of those steps are on the same order as the time scales of the process, right?
Well, they are.
Yeah. But that makes that's going to make the analysis interesting but challenging, I think.
Yeah, but to estimate it sort of while it's taking on, that's very hard, I think. But once the epidemic is over, you can learn from it. So what did people do? Try to estimate this and see which played an effect and which did not.
And that should be more and more possible as data collection becomes easier. Yeah. Thank you. Thanks.
You're the chairman, Eric, so you shouldn't raise your hand.
But I wanted to ask the question in following up on this. One question I had here was in regard to rewiring. What if individuals chose not to rewire to anyone? Or maybe a little more subtle would be, what if there was some possibility that someone took like a celibacy measure versus rewiring to another sexual partner?
Yeah, so there was that was possible in the model. So I had the parameter which I called alpha, which was a probability. Alpha equals 1 was that if you drop this edge, you always rewire. Alpha equal to 0 says that if you drop it, you never connect to someone else, and you can have some. So we treat both those situations. I think there was someone.
So, are you going to attempt to fit this to HIV data? Because you mentioned that as an example. And what other effects do you think might matter for HIV in particular?
Well, the HIV, I wouldn't say we're in the initial phase of it now, though, are we?
No.
But it's not that I have HIV particularly in mind, but possibly, that's something I aim to do, not sort of next week. The next step, I will add some additional preventive measures to see how that affects things, and then look at possibilities to estimate this, and then try to find which diseases would this be relevant for. Yeah.
And what do you think happens with diseases that sometimes act in tandem, like HIV and pneumonia? And like you get one and your immune defense system goes down, and then there's another disease which kills you. Is it possible to model things like that together, or has anyone done that?
Pneumonia and HIV, I don't know, but TB and HIV are also related. I know. I think there are models for that, but probably more sort of theoretically modeling. You have sort of competing epidemics, but also what's the opposite of competing? Sort of epidemics that help each other. There are models for that, but I'm not sure if they have been implemented for data analysis. Am I the chairman, or are you the chairman, Eric?
Feel free to get it out of this corner here.
All right.
Go ahead.
No, okay.
No, go ahead.
So, from a statistical perspective, do you think that you...
Speak louder. I hear what you're saying, but the others don't.
Okay, so from a statistical perspective, do you think you would get access to the dynamics of the graph, or only its...
No, that's an important thing. I don't think you could. You could get some what's called egocentric information about the network. So you could possibly get how many partners have you had, and I think at least in Sweden that is collected. Once someone is diagnosed with HIV, they have to name their partners because there is you have to trace to test them. So you could get some partial information, but and if it's let's think of Ebola households, I think that information is available. So you probably have some partial information about the network, but of course not complete. In Tom Snyder's talk, he had complete information about the network. Then, of course, that helps the statistical analysis, of course. Yep.
I have a question. Why can't you start from the middle of the epidemics? You will have just start from the point where you have certain number of nodes affected, I mean already sick, and then go from there.
I wasn't able to do that analysis, but maybe you are, so you're welcome to do it.
I'm just asking what is the theoretical, basically what is the problem, methodological problem here? I mean, if you're starting from the middle rather than from the beginning, because you have certain number, say, of nodes affected, maybe some susceptible, some...
Yeah, but it takes place on a network. That is what complicates matters. And how the disease propagates depends on the local features of the network. But I can't say more than that. So it's not all that easy to analyze it. And without rewiring, it has been analyzed what will happen to the end. But when they analyze what happens to the end, you start at the end and sort of look backwards in time. Who could have infected me? And you sort of forget time. That's called susceptibility sets. Which are my neighbors and my next door neighbors and their neighbors that could have infected me. So that's also done using this branching approximation. But to analyze the dynamics of the network over time is too complicated.
But am I right in thinking that you rely a lot on the assumption that nobody else is infected yet? And that is why...
By branching process, yes.
Why making the approximation in the start is easier than
Yes.
the middle?
The only, if you become infected, you will see only susceptibles except your infector.
Exactly.
Ah, okay.
Yes?
Okay,
You answered my question.
so I had a technical question basically. So the pairs approximation, that obviously will kind of is this moment closure idea.
Yes?
Well, you can expect that for count data, and especially in the very beginning. So I guess when you look at the number of infected, it won't be very good. It will be, have high skewness. But you could actually correct that, I guess, by just going up to higher orders and avoid this moment closure at level 2. You can go to 3 or 4. Would that improve things, you think?
Probably. I mean, I'm not an expert, but the first is the uniform mixing situation where you just keep track of the numbers. But now if you take into account also the pairs, that improves things. And probably if you keep track also of the triplets, but close after that, my guess is that you will come closer to the reality then. But it's nothing that I have studied in any extent. There are a fair number of triplets. You have a fair number of differential equations to keep track of.
Yes, you would have basically all. Yeah, it's quite a number, but yeah. And it's good packages to solve.
Yeah. Numerically, yes. That's. I think you could do a good job there.
Help Tom nearly use his entire hour. Okay, let's thank Tom again.